Whoa, order.
Concentrate, guys. Come on.
Yes, you carry on that rate, you won't be able to do anything.
No, we'll fail.
You won't be able to draw a graph.
Especially you, Jimmy.
And you, Bobby.
And you, Jimmy Bob.
And you, Sarah.
Yeah. I don't
cry.
Someone get her a tissue.
Just give her that.
Yeah, she seems fine now.
So in case you didn't get it, we're doing orders of rate concentration graphs. There was a few puns we could have made about it, so we went with the worst one we thought.
Yeah, that which was bad. Anyway.
So we're getting on with it.
So, in the graph, we're going to do out nibble on axes, good starting step.
Yep.
Rate against concentration.
Yep, so it's not concentration against time, it's not the same thing.
Yeah, it's not.
But this particular graph can be useful for determining from a graph if it's going to be first, second or zero order.
So, let's go for that. So we're going to have
3 different colours, I like it.
0. This is shorter. First
and second order things. Now, a rate against concentration graph can be determined if you look at it as to what a particular thing is. But for that, you need to know what they look like.
So, best way I think to do about this, you can just learn them. I like thinking about them.
Yeah.
So, if for zero order you increase the concentration, it won't affect the rate.
So as this increases, the rate will stay at a constant value.
So, you can just draw a straight line across.
Just like that. For order 1, if you increase the concentration, the rate goes up accordingly. So if you decrease it all the way to 0, there'll be no rate.
Yeah.
And for every 1 up, it will go 1 unit up. And so it's just going to be a linear straight line upwards.
Like that, and then finally, squaring it. You square it, it'll become a quadratic, if you're familiar with those, an exponential.
Yep, so it'll still start at 0, and then it will just rapidly increase exponentially. And this can be useful if this is a graph of, I'm going to draw in red to correspond with this. If this is a HCl concentration, hydrochloric acid in any reaction,
yeah.
Just say I'm making this up, but if it tells you that,
then you know that HCl is second order.
Because you know it looks like this, and that's a second order thing. So you can then say HCl is second order without any information.
Which is pretty darn swish. But they might not give you a graph.
They might give you a table.
So just in case they give you one of those, we'll give you some chairs and you'll sit down and think about it.
That was a good pun. That makes
Thank
up
you.
for the
That makes
terrible
up.
intro.
I think it does. So
Sarah's now laughing.
And existing.
That's good.
So if you have concentration of a couple of things.
Yep. Let's just make it a nice simple A plus B. You can get 3, but we'll just go with 2 for now.
And then let's say rate.
Yep.
So I'll give you all the information. You have to work out the rest for yourself. So
Okay.
say at the start your rate is 3 when these two things are 0.1 win.
Okay, so what's happening here is both of the concentration of A and B is 0.1 mole per decimeter cubed. The rate of reaction with that is 3 mole per decimeter cubed per second.
So what would you suggest to do to be able to work out the orders of these two things respectively?
Well, what you can do is you can treat this as a control, and what you can do is keep one of the things constant, so this could stay at 0.1, and say double the other, something easy, so 0.2, and then see what happens to the rate of reaction.
So, for example, it could turn to 6.
Now what I've noticed, if this is doubled and this is doubled, then that means B must be order 1, because it's increasing accordingly. You're doubling that, this is also doubling.
So then, if you tried the other way round, say you doubled A.
Yep.
And kept this
If
one
you
the same.
double A, it'd be 0.2.
Sorry. No, I meant. And it became 9.
Yeah. Then, because this is doubled and this is squared,
then you can say that is a second order.
often in your exam, just a hint for you here, Wayne's top tips, you're going to have 3 things. You might have a concentration C.
Yeah.
They'll double that and nothing will happen.
And that will mean it's 0 order.
Sometimes you have to look carefully at what's going on. Now, if you were to do this experiment, which you might do in your chemistry lab, it doesn't actually matter. If you started this at 0.2 and the other at 0.1, it doesn't matter that they're not the same. This is still a control. You still double that. It's just that would be 0.4 when you double it, and it would still increase accordingly. And that would go back to 0.2.
Yeah, so the control doesn't really matter what it is as long as it's something.
So it's just worth mentioning. These do not have to be exactly the same.
But now you know the orders, then you can go through and do what we described in the other video, working out the rate and then the rate constant and that sort of thing.
The only extra thing here is the temperature effect on the rate constant K.
Yeah, just before we go on to that, they could give you a big table with a few things that will be able to tell you what rate they are, and then it might say rub out sometimes. It might have a fourth column where this is 0.4 and this is 0.2, and they might not say this, and you have to write down the value for it, but then you're applying your knowledge that you've known. But that's all, yeah, on to the next bit.
Yes, so the effect of temperature on the rate constant.
So, it's a thing you just have to know. It is always this way. This part of the exam is a bit confusing because we do rate of reaction of like this, we do rate of half-lives, and we do rate of equilibrium. And they've all got K's in them, so you have to know which K you're on about.
Yep. So if it says the rate constant, then it's this one.
Yeah.
So I'm using this particular example.
Okay.
Although we said that A is squared and B is 1 in this example.
But
like
yeah,
that.
like that.
You know that if you increase the temperature, you're going to increase the rate because there's going to be more successful collisions.
Yeah, more collisions and then more likely to more successful collisions.
So if the
It's a
rate
GCSE thing.
increases and K equals rate over the concentration,
Then K must increase as well.
because these are going to stay the same, the concentration of them isn't going to change. So if that's increasing and they're staying the same, this must get bigger.
It must.
And in fact, I have drawn that up in the top corner, we'll draw it here, K against temperature increases like that.
Which is pretty cool.
It depends on the activation energy as to where this will cut the y-axis. You don't know much about that, you won't be asked to plot it, but you might be asked to state the relationship. As K increases, as T increases, K increases.
Yeah.
There you go.
There you are. So that's all that stuff. And now we're going to get on to the rate determining step, which is very exciting, except it's not very. And then the evil equilibrium.
Yep, and then a cup of tea.
And then a cup of tea, and then I think we're going to wipe out the dinosaurs.
Yeah.